Good morning. Myself, Sruthi Vishwanath, Assistant Professor, Department of Science and Humanities, Vedavyasa Institute of Technology. Today, I welcome you all to the Tech Talk session on biomedical applications of PVA based hydrogels. In this presentation, I would like to include what is hydrogels, some important applications of hydrogels, speciality of polyvinyl alcohol and polyethylene glycol, preparation method, experimental techniques, and biomedical application. What is hydrogels? Hydrogels are three-dimensional hydrophilic water-insoluble polymer network. They are able to absorb a large amount of water and can swell in water while maintaining the structure due to physical or chemical cross-linking of individual polymer chains. The water holding capacity of the hydrogels arises mainly due to the presence of hydrophilic groups such as amino, carboxylic, and hydroxyl groups in polymer chains. Due to peculiar properties of hydrogels such as high sensitivity to physiological environment, hydrophilic nature, soft tissue applications like water content and adequate flexibility make them excellent candidate for biomedical applications. Some applications of hydrogels. Hydrogels in tissue engineering, hydrogels as barrier, hydrogels as scaffold material used in wound dressing, as contact lens and used in drug delivery. Polyvinyl alcohols. PVA is produced by the polymerization of vinyl acetate to polyvinyl acetate followed by its hydrolysis. It has relatively simple chemical structure with a pendant hydroxyl group. It is non-toxic, non-carcinogenic, high hydrophilicity, biocompatibility, good chemical resistance, and good film and gel forming ability. One of the most successful tissue engineering applications of PVA is in vascular tissue. PVA hydrogels are articular cartilage replacement by examining physical aspects including lubrication, load bearing, biocompatibility, and attachment of the material to bone. Polyethylene glycol. It is considered as a safe chemical due to its non-toxic nature. PEG, with its biocompatibility, flexibility, and stealth properties, is an ideal material for use in biomedical applications. PEG has various uses in the medical field, including drug delivery, treatment of hepatitis C as laxatives, for cell immobilization as addition promoters, biosensor material, and for encapsulation of islets of Langerhans for treatment of diabetes. PEG hydrogels have been the most successful synthetic gels for tissue engineering applications. Next, we move on to the preparation methods. Prepared 5 to 20 percentage of PVA in water at 90 degrees Celsius in a thermostat. Cross-linked with the PEG at 70 degrees Celsius. Cooled at the high viscous fluid to 30 degrees Celsius. Sonicated at 30 degrees Celsius for 15 minutes. Cooled to minus 20 degrees Celsius with high cooling rate in deep freezer and kept for 15 hours. Thawed to 30 degrees Celsius and kept for 5 hours. Repeat the freeze thaw cycle 3 to 5 times. The freeze thaw method, that is the main method to prepare the PVA based hydrogels. Then experimental techniques. Degree of swelling. Degree of swelling could be described as water absorptivity of the hydrogels. Degree of swelling declines as the PVA concentration goes up. As the PVA concentration increases, the number of PVA molecules in a unit volume becomes larger. More enlarged zones are produced and the distance d, that is between the PVA crystallized, is diminished. It is observed that the gel swell to high extent in the first few minutes. After that, there is a considerable variation in the swelling rate, the effect of PEG in swelling rate of PVA. PEG is also occupied some space of the pores. Ultimately, it leads to decreasing swelling rate. Next, gel fraction analysis. Gel fraction increases with increasing the concentration of PVA and PEG. The concentration of PVA increases, the number of PVA molecules in a unit volume become larger, and that will create more entangled zones. Creep analysis. the PEG concentration is increases, the creep resistance is increases because more hydrogen bonds are formed between the ingredients. As the gels are prepared from PVA and PEG, the gel pores are occupied by the PEG and water. Ultimately, the equilibrium water content of the gel decreases and it leads to increase in creep resistance. At last, conclusion. Hydrogels represent an appealing class of biomaterial for tissue engineering applications. A significant disadvantage of PV hydrogel is its low mechanical strength. This could be effectively solved by the PEG cross-linking. Hot mixing of the components is very effective for compounding and that will provide homogeneity and better mechanical properties and improve the creep resistance. The gels processed in the presence of PEG exhibited a significantly higher total creep resistance than the processed gel without PEG. This can also be developed as an engineered cartilage for potential implants, considering its viscoelastic properties. It's developed as an engineered cartilage. That is the main application of PVA based hydrogels. That's all about the PVA based hydrogels in biomedical application. Thank you.